Today we are looking at a company that claims to have solved the error correction problem. And if you want to learn more about why this is the case and how they are actually doing it, then stay tuned because today we are looking at Quantum Circuits Inc. And with that, let's hop right into it. Let's start checking out their website. So here we are at the website of Quantum Circuits Inc., where, as it says, very small here, QCI. And what we see is, first of all, this very nicely animated chandelier here with all the radio frequency lines going down here where I guess the quantum processor would be sitting. And it says quantum, stability, repeatability, and consistency. We invented the first dual rail qubit with built-in error detection and control flow that resets the standard on quantum performance, efficiency, and stability. We are paving the way to a fault-tolerant commercialized quantum computing era. And then here you can learn more about the technology, and we will definitely do that in a second. But before we do so, let's quickly go through the information that we can find here. So the path to commercial-ready quantum computing must be error aware, results must be consistent. We are delivering both. So conventional NISQ, which is, let's say, the era that we are in today. These are devices that have that are prone to some types of errors. Then detection with erasure qubits. So this is a system, and that's, I think, where they are based right now, is a system that is aware of errors, it can detect errors and then, I guess, mitigate or act on these errors. Then there's partial error correction, and finally there's fault tolerant error, where basically you use many physical qubits to build a logical qubit that is fully error corrected, which means if for some reason you are collecting some issue because you're not, let's say, fully rotating your qubit from a 0 to a 1, but maybe have a little bit of offset, the system is kind of treating this error, is correcting this error so that it doesn't spread by creating superpositions over the whole system. And that's being done by adding a lot of let's say, physical qubits into one logical qubit. Very quick note on that. I will not go into the details of it today, but why can't you just copy qubit information? Why can't you just do something like, I don't know, an array system where you have multiple drives and then you have, let's say, one correction, or you have a mathematical function that ensures that you are not collecting an error. That's because of the fact that you are entangling these qubits, so you're delocalizing this error, you're spreading it over the whole system, so it's kind of hard to identify where exactly the error is happening, and you cannot just copy information because of the non-cloning theorem. So you have to come up with ways to measure the qubit without measuring the qubit. So you want to know if there's an error in some way, but you cannot measure the qubit because otherwise you're destroying the properties, and you cannot just copy the qubit and measure the copy because you cannot copy any quantum information. So it is a very intricate process. It requires a lot of, let's say, know-how. There's a lot of theory behind that. It's a very complex thing, and that's why this is, let's say, a little bit further in the future, because you need a lot of physical qubits to actually build these algorithms. Going from the NISQ era, where the devices have some errors, this is, let's say, the first step. So how does it work? So the industry's first dual rail qubit with built-in error detection. Quantum Circuits is a full stack system using breakthrough superconducting dual rail cavity qubits with built-in error detection and control. It features a robust programming interface for developing new algorithms and exploring quantum in novel ways. This enables real near-term applications and a path to quantum advantage through efficient error correction. The new features: no other quantum company offers the combination of these three features built into the qubit and hardware levels. First one, quantum error detection. So based on innovative superconducting hardware design, built-in error detection at qubit level enhances system performance through active detection, tagging, and appropriate processing of the system's dominant quantum error channels, and unlocks a host of algorithmic development possibilities. And here you see these. So usually I think they're called ancilla qubits. You have, let's say, a qubit that is doing somehow the computation, and then you have a second one which you are kind of using as an auxiliary qubit to actually detect if something's going wrong. So you have these two lines here of the two qubits, and it says here error detection, and Q0 in code space. And then as the time progresses, you have some operations going on here. Then it says real-time control flow, RTCF, a toolkit to tightly couple classical quantum programs, so measurement-based feedback, conditional branching, real-time qubit reset for reuse and calculation, arithmetic, dynamic gate parameterization, and runtime looping. So this is on the programming side, I guess, like how the handling of these operations, of the measurements and on the detection is being done. And then finally, the error detection handling, methods to manage detected errors in real time. So mid-circuit erasure detection, end-of-line measurement per qubit, real-time control flow coupling, and then user-controlled post-selection. So this is, I guess, what happens, as it says in the name. If you're detecting an error, how are you handling it? On the key benefits, so fast, high-fidelity algorithm execution, achieve high throughput with feature-rich software and hardware, reducing waiting time and increasing productivity. And that's, I think, one of the, let's say, major advantages also of the superconducting technology is that you can actually that you can run those algorithms pretty fast. So it's not like you take you can run those on a very, very fast scale, and that enables you to run many of those requests on the system without having to wait for too long, compared to other technologies where you first need to initialize, excite, wait for states to decay, like with optical accessibility and things like that, or physically move atoms around. That is something where superconducting technology has some advantage from my understanding. Then it says efficient quantum classical integration, utilize unique programming with looping, branching, and classical computations for seamless integration and high fidelity, and then enhanced algorithms with error detection, incorporate error detection into quantum workflows to expand algorithm possibilities and enhance value creation. Lighting the way, explore with us, hold a candle and see it clearly, place it 100 yards away and you see a flicker. But put in the moon and it vanishes from eyesight. That's how difficult it is to detect a single error, but quantum circuits machines can still do it with precise error detection at the qubit level. We lead in delivering powerful, scalable qubits with built-in error detection. Don't miss the next tech wave. Quantum Circuits invites you to join our alpha program and execute quantum applications on our hardware with error detection. It's a pragmatic, methodical way to accelerate your own path to commercial quantum applications. And then you can start now. So here you can learn more about this alpha program. Then we see some partners here, and I'm not going through every single one of them, but I'm just pointing out that some of those you've probably already seen in the Hidden Quantum Champions playlist. If not, make sure to check that out here on the YouTube channel, because many other companies from the ecosystem are featured there. For example, from this page, Q Control, which has earlier been featured already. Then we see the investors here. And as per usual, there's also some highlighted articles here to discover more. With that, we go up again and check out very briefly the technology side of things. So again, we see a very cool animation here in the background, very artistically high valuable, like very cool. I like those. It says technology, detect correct scale, introducing quantum computing's first dual rail qubit with built-in error detection. We take a more pragmatic approach. We correct first, then scale. In quantum computing, two ideologies drive innovation of qubit efficiency: scale first, then correct, and correct first, then scale. We are proving that correcting first, then scaling quantum performance works much better. It's more pragmatic. It leapfrogs the focus on conventional brute force qubit volumes, accelerating the path to commercially viable, fault-tolerant quantum computing. Quickly take a step back and talk about these two paradigms. So scale first, then correct versus correct first and then scale. So the scale first and then correct idea is exactly that one. So you create a system that has many qubits. You don't care too much about the single qubit quality. And then the idea is that, okay, later on we put the error correction kind of on top. We play the error correction algorithm on top. And with that, we can remove those errors again, so that like it doesn't really matter if every single qubit individually creates a lot of errors. The other side is correct first and then scale. So you have, let's say, a lower number of qubits, but these ones, they are, let's say, less noisy because they are intrinsically corrected. There's some error mitigation ongoing. The quality of the individual qubit is pretty high. And then with a lower number of qubits, you can actually already do something. You can run some gates on those. And because of the fact that they are, let's say, higher quality, what comes out is also something that is usable. And now the question is, on the one hand, you have, let's say, something that is scaling fast, but the utilization is moving up a little bit slower because you need to have this error propagation on top there, right? And there's like some gap between those. On the other side, you have something that is scaling much slower because you need to make sure that every single qubit has a certain quality so that you can work with it properly. But then, of course, every qubit that you add is immediately a qubit that you can use for something. And that's, I think, also what you see if you're looking at, let's say, the bigger companies in the space. There are some that are, let's say, going brute force into we need more qubits, more volume, higher quantum volume, or whatever you want to call it. There are also some exponential law ideas connected with different people's names that kind of amplifies on this, that like the number of qubits is supposed to go up exponentially. And then there are other ones that say, okay, we need to make sure that every qubit that we add here is a high quality, lowest possible error one. And that's, I think, where QCI is also in the philosophy side of things. So here you also see it, I think, against each other. So you see lots of noisy qubits, conventional NISQ approach, error mitigation has scaling challenges, brute force, inefficient qubit volumes, and then quantum error correction is a heavy lift. On the other side, you see qubit designs to efficiently detect and correct errors at scale, feature-rich, error-aware quantum programming, validated path to scalable quantum systems, hardware efficiency with dual rail approach, and then simplified quantum error correction. Now on the dual rail qubit, powerful qubits architected for scale, it says Quantum Circuits is a full stack quantum computing provider using dual rail qubits technology. Our systems leverage superconducting circuits for fast and reliable algorithm execution. The core is the quantum processing unit, QPU, based on DRQ technology. So that's again this dual rail qubit technology, right? Which uses pairs of superconducting cavities to encode quantum bits with microwave frequency photons. This architecture supports quantum error correction, QED, enhancing performance by actively detecting and processing quantum errors. It opens up new algorithmic possibilities and provides an efficient path to scalable quantum error correction. And here is kind of what it looks like. So you have measurement, you have the two transmons, then they are coupled, and there's like these cavities. And here you see this photon, this microwave frequency photon. Quantum error detection, so how does it work? You see the different qubits here, you see the different, I guess, control lines, and then it says quantum error correction increases application performance by boosting fidelities over the native properties of quantum hardware. Cavities have a known dominant quantum error channel called single photon loss, leading to erasures or errors on known qubits. These are less damaging errors a quantum system can experience. DRQs enable detection of erasure events with high fidelity. The record of their occurrence can be discarded from the output data record through a post-selection process, making QED hardware native to the DRQ architecture. Benefits are superconducting cavities have several advantages which reduce the resources necessary for error correction, fault tolerance, and quantum advantage. High coherence times, very favorable error profile with cavities, and error convert to erasure in known high fidelity ways. And then there are some more information here on the real-time control flow. So how does it actually work? Real-time control flow allows users to execute advanced classical operations in parallel with quantum systems, from basic branching on measurement results and arithmetic to runtime looping and dynamic gates. Such classical quantum or coprocessing enables new types of algorithms and streamlines quantum error correction resource requirements. It also tightens the coupling between classical and quantum calculations. Leveraging RTCF enables efficient and fast application execution. This is crucial for variational algorithms that require large volumes of data, thereby cutting costs and increasing throughput. I will not let's say explain the whole framework now around what are cavities, what are 3D and 2D type of cavities in superconducting systems, and what are transmon qubits and so on. If you're interested in this, let me know down in the comments below. I'm happy to make a particular video about this specific topic. What I want to quickly mention here is this note that you saw in here in this text, which was on the variational algorithm. So that is very much in the space of, let's say, optimization problems. Could be, let's say, I think there's like AI ideas of how to use variational algorithms, but can also be other stuff that can be mapped onto those. Just want to point out that like here you see already some indication that this system might be interesting for a specific type of algorithm group. And this is not only true for this system. I think this is something that is generally valid. So there are certain systems that might be a little bit slower in execution, that might have a little bit less qubits, but therefore are very stable, which means you can, let's say, do a longer amount or a higher number of gates in your algorithm, so deeper gates. There are other ones that have more qubits but less coherence, and therefore you can run on many gates, but not, let's say, run very deep algorithms because your coherence is getting lost. There are systems where they have a lot of qubits, but not every single one is physically connected to each other once. There are other ones that have different architectures where like different qubits can be connected. So you see there's like a high variety on how these qubit layouts are actually being done and what types of advantages and maybe also disadvantages these have. So depending on the type of algorithm you're looking at, a different system might be a better fit at this point in time. Of course, in the future, if there's a system that is, let's say, fully error corrected, that runs on fully logical qubits, this might look a little bit different. Still, there will be certain ones that have more or less qubits, but then, let's say, the depth, for example, of your circuit is not such a big thing anymore, and therefore maybe also not the topography, because if you are just running a lot of gates that are bringing qubits into superposition, you can still spread your superposition across the whole chip, and you don't rely too much anymore on the architecture that is sitting below. But for now, the architecture is playing a big role, and that's something that is to be put out here. Last point down here, so error detection handling, EDH. Error detection handling is unique to the quantum industry. It allows users to explore previously inaccessible class of algorithms. Users manage QED themselves. Feature include custom placement of error detection meters in algorithm, RTCF to branch on error results in addition to the typical binary qubit measurement outcomes, and then tailoring post-selection analysis routines to access error data in fundamental, new and flexible ways. These unique capabilities enable users to explore algorithms that use error information as an asset and over real-time control in their quantum workflow design. There is also some information here about the product, which is the system, I guess, the full stack system. As per usual, we see there are like different tiers down here. So we see the Acumen Seeker. Acumen Seeker is the industry's first dual rail cavity qubit quantum computing system. So this is the system. There's a simulator available as well, which you can use to simulate this system, to simulate algorithms. Then there's a cloud service, so you can probably access the system itself via the cloud. So the Acumen Cloud Service, ACS, is an out-of-the-box quantum as a service that delivers a seamless platform for users to run. And then there's the Acumen SDK, which is a collection of Python libraries, documentation, and examples that empowers users to execute quantum applications on quantum circuits, QPUs, and simulators. Its QCDL programming environment offers maximum flexibility, unlocking a rich feature set, real-time control options, and error management with EDH. The SDK connects users to the Acumen Cloud Service. Everything submitted through the SDK can be monitored via the cloud portal, enabling a seamless, efficient, and transparent workflow experience. And then there are also some APIs here available, as in how do you actually program something on the system. So there's the QCDL, then there's Qiskit, which is the open source language from NVIDIA, and then there's CUDA-Q, which is Qiskit from IBM. Sorry, I was already skipping to the next one. And then there's CUDA-Q from NVIDIA, of course. Okay, and then quantum circuit application examples. So these are, let's say, examples how to use this. So efficient phase estimation, enhanced quantum algorithm, building block for drug and materials design, finance optimization, and cryptography. I guess that goes into the direction of this variational stuff that we've seen before. But yeah, not an expert on that, so I wouldn't, let's say, fully rely on that thought. Then there's enhanced NISQ applications. So it's a struggle to obtain quantum advantage from NISQ quantum algorithms for chemistry, simulation, machine learning, and operation research, even with error mitigation. Running same NISQ algorithms with built-in error detection enhanced performance. Useful quantum advantage may become viable sooner. And then correcting detected errors. Errors detected, corrected with extremely low overhead of only 5 dual rail qubits, and so on. Our differentiation built-in error detection like no other, and there is again some explanation down here on the technology. With that, as per usual, let's quickly check out this Explore site here as well. So there you can get in touch with them for the program. If you want to, for example, start using their systems, I think this is your way in here. There is also something here on the perspective. So I guess this is the news articles, which is fairly up to date. I'm recording in December 2025. You see there's some news here from December 2025. So the not so surprising power of error detection, efficiently leveraging error data with dual rail qubits. But there was also some announcement about collaboration with NVIDIA and other collaborations down in here. Additionally, there are some resources which I guess is, as per usual, related to topics like relevant for the company. So Here you see Quantum Circuits secures more than $60 million in Series B investment round. Final closing of funding round follows hiring of CEO Ray Smets, reinforcing industry first paves faster path to commercial ready quantum computing. So there's some information about that, and the collaboration with NVIDIA. I think there's a lot of information here about this collaboration with NVIDIA, but also algorithmic. Let's quickly also look into the company. So learning a little bit more about that as the last chapter of today's video. It says knowledge, our quantum story. So Connecticut, New Haven. I'm not a geographics expert, but I think that's like probably indicating that the company is based in the US, and New Haven, I think, is somewhere close to New York, if I'm not confusing. So at the East Coast, I'm pointing in that way, but probably for you it's the other direction, East Coast of the US. It says, welcome to Quantum Circuits, built by the pioneers of the superconducting quantum computing field. Quantum Circuits was founded in 2015 by scientists from Yale University, including Sterling Professor Rob Schulkopf. Rob is widely regarded as one of the pioneers in the superconducting quantum computing field. Many of his students have gone on to start quantum companies or join quantum teams at large enterprises like Google, IBM, and Amazon. Many joined him at Quantum Circuits. Much of the industry's knowledge originates from Rob and the founder's curriculum. Over the years, Quantum Circuits did not project publicly. That was intentional. We avoided marketing visionware, focusing on hastening the path to commercial viable fault-tolerant quantum computing. We believe there is a time and a place for everything, including publicizing our industry-leading approach and solutions. That time is now. Quantum Circuits is the company that no one heard from before, but everyone must know. And that's, of course, why it's part of the Hidden Quantum Champions, because we are featuring here exactly those companies that everyone should know about, but probably no one heard about that. So, welcome to Quantum Circuits. Welcome to the place where the world's leading quantum scientists make successful strides towards commercializing quantum computing. We are the leapfrog who jumped ahead of the industry with the first built-in error detection at the qubit level, paving a better, higher fidelity approach to improving performance and efficiency without requiring brute force qubit volumes. We are not concerned about qubit arms race or being the first to proclaim the functional quantum computer. We focus on what matters most to business, economy, and humanity, achieving stable, fault-tolerant quantum computers that deliver consistent, repeatable results that can be trusted. Only then will we solve what was once unsolvable. Explore it with us. And then there's, I think, some comment down here. Achievements, like, for example, I guess awards, National Academy of Science. So I guess some awards down here as well. And then we see the board. So there's the executive team. We've heard about the CEO before, but we also see the professor that we've read and others. So chief technologist and co-founder, VP of software engineering. So very technical driven, let's say, side here. But we also see, of course, there's like head of marketing as like for a proper company. There's a board of directors in here as well, and then there's an advisory board available as well. There's some information here on the investors that are part of this company, and I think with that we are already moving towards the end of today's video. And I mean, I hope you liked it. I think it's a very, let's say, unique perspective. It's something that we probably haven't talked about too much in this series. So this is the perspective of error correction, probably as soon as possible. I hope you liked it. If so, please make sure to subscribe to this channel so you don't miss out on the next video. And give the video thumbs up if you made it all the way to the end. I'm excited to see how many people have actually watched it until here. As per usual, make sure to stay hydrated, and I'm looking forward to see you in the next video. Until then, bye bye.